Okay, so here's what we were talking about last time. So double integrals. Here's an example of the kind of problem you might be interested in with solving with a double integral, and it's compute the volume under this surface sitting over that triangle, right? And we developed this the answer to this question, and we talked about how this volume you can look at it as an integral of slicing area, and blah blah blah. We end up with a double integral over this triangle. Then we made the observation that the process of converting a double integral, we know the volume can be computed as double integral of f dA. The process of converting that into an iterated integral, a dx integral of a dy integral. Right. In this process, there was two pretty notably interesting observations. One is the integrand is the same for both. Right. So we don't need any visual representation of the integrand if for the process of converting a double integral that we know is the answer to our question to an iterated integral, which is something we know how to compute. Right, so this is an important transition. For that transitional process, we don't need to know what's happening to f. We know what's happening to f. Absolutely nothing is happening to it. It's going to be the same integrand, right? So all we really need to do then is to figure out what are these bounds. What are the bounds that go on these nested integrals? And we made the case last time, I think this is pretty believable, that the bounds all come from looking what's happening down in here, namely entirely comes from looking at the domain, whatever that domain is, for the original double integral. And the domain is two-dimensional, not three-dimensional. So the punchline here is, the realization we made at the very end of the last lecture is this picture is unnecessarily complicated for the purposes of what we're doing here. We don't need to draw the actual volume. We just need to draw the domain to find those bounds. The integrand is obvious. So this is the better picture to draw. Here's that domain again. Here is that domain again. Same domain. And we just need to draw, what's that slicing process look like? Well, as I do my outside integral, as x goes from 0 to 1, here's what slices look like. Right? And I know my starting value of x is there, my ending value of x is there. Easy to find those bounds. Then for the inside integral, as I go across one of those slices, my starting value of y is determined by that point. A little geometry tells you where it is. The ending value of y is determined by that point. And again, a little geometry tells you where that is. So this is the much easier and much more desirable picture to deal with. Okay. All right, so let's work some more problems along these lines. Here, very analogous kind of question. Let's look at the volume under a graph of this function. Okay, now pause right away. Right away, we're looking for the volume under a graph. Right away, I know that volume is computed by a double integral where the integrand is the function whose graph I'm looking at. I don't even need to read the rest of the question. I know already that double integral is going to give it to me. I don't even need to draw a picture. I mean, we've done a bunch of these, right? So volumes under graphs are double integrals over the domain of whatever you're looking at the graph of. So, boom, we already made a little bit of progress. Let's see. Further, I know that double integrals are going to turn into iterated integrals. I know that the integrand is the same, right? So I haven't even finished reading the question yet, and I already know practically everything about the answer. Does everybody see what I did there? Okay, so what remains, as before, what remains is to figure out these bounds, upper and lower bounds for the four upper and lower bounds for the two integrals in question. And those bounds, of course, are going to depend on the domain, and the domain is, let's read the rest of the question, the region in the xy plane bounded by these two curves. Okay, so here's where we have to actually draw a picture. Let's look at the region in the xy plane bounded by those two curves. And of course, we all remember high school algebra. These are parabolas. One's sort of right side up, the other's, if you will, right upside down. So our picture is this. Okay. All right. Now, this being our domain, I'm going to slice as follows. By the way, I'm going to make an arbitrary choice, a semi-arbitrary choice of which way to do the slicing. Remember, you do have two choices. You can do your, what you might call your X slicing first, or you could do your, what you might call Y slicing first. So, semi-arbitrarily, asterisk, come back and talk about that later. I'm going to do my X slicing first, so you'll notice that as I move in the X direction, these are what my slices look like. And I hope you can see from the picture that my starting value of X is determined by that point. My ending value of X is determined by that point. And again, our usual process will help us find what these values of X are. The bounds are determined by points that you can identify in your picture. Points are identified by curves. This point here, for example, is identified as, well, it's the intersection of that curve with that curve. Those curves have equations. Now I've got some algebra to solve. Right, so again, it's always in that order. Bounds that you're looking for, find the associated point. That point is on what curves? Those curves have what equations? Now that you've got equations, do your algebra. Okay, now in this case, again, reminder, we're trying to find bounds for X. We're looking for X bounds. So I need to solve for X in this pair of equations. Notice that in these two equations, I've got Y equals. These, at the point in question, that Y is the same as this Y. So that means I need X squared equal to 2 minus X squared. And again, a little algebra. There you go. Okay, is everybody on board? Is everybody happy with that process? Okay, so our X bounds. X, and the way I like to write this, the X bounds, -1 to 1. So highlighting in green there to identify the, what's going on with the X integral. X goes from -1 to 1. Okay. All right. Now, for a given value of X, so we're going to fix X. And for the rest of this question, X is not allowed to change. We're just looking at that X slice. Call back. If you prefer, if you feel more comfortable thinking about three-dimensional pictures, we are now looking at, for this value of X, and, why are we interested in the range of values of Y for that value of X? Well, because we're trying to compute this, again, back to the volume point of view, we're trying to compute the cross-sectional area of this thing. The cross-sectional area of this thing is going to be an integral as Y ranges, and I need to know the range of values of Y for that X. How far does Y range? Because that's the domain for the integral that will define that cross-sectional area. That's just a reminder. It's just a lot easier to think of it as we're slicing up this triangle, and for each value of X, we need to know the corresponding range of values of Y. Okay. Right, okay, so for this value of X, what's the range of values of Y? Well, Y, the lower bound for Y, based off of that point. That point is on that curve, which has that equation. Keep in mind what we're interested in. We're trying to solve for Y. So I need to solve for Y in that equation, and I need to, how are we going to solve for Y in this equation? Well, lucky break, it's already been solved for. Sometimes things just fall in your lap. It's nice, right? It won't always. Sometimes you get lucky, and we got lucky here. So the bound is based on a point. The point's on a curve. The curve has an equation. Solve for the variable you're interested in. There it is. So our lower bound, our lower bound for Y right, as y varies, our lower bound for y is x squared. And you'll notice I have that as, for my y, lower bound for y is x squared. Same game for the upper bound for y. So again, as y varies, for this fixed value of x, x is still fixed. The upper bound for y is based off of that point. That point is on that curve. That curve has that equation. Again, don't forget what you're interested in. I want to know y. Solve for y. Again, we got lucky. It's already solved for. There's your upper bound, 2 minus x squared. Okay. So, x squared to 2 minus x squared. Is everybody happy? Okay. All right, now one other little thing we have to think about, and that's a minor, just a reminder. We've already agreed that the function whose graph we're looking at, that's the integrand, and so don't forget to carry that through. I mean, again, that's just a sort of a bookkeeping thing, but that is, in fact, still our integrand. Okay. Okay, here's another example. There's a lot of examples. There'd be a lot of examples in today's lecture, by the way. It's easier to kind of get a feel for these things by just doing a bunch of them. So that's today. Okay, so I want to find now, this is a twist on the problems that we've been doing. Suppose we want to find the volume that's bounded between two particular surfaces. So, a couple of weird things about the way this question is phrased. On the one hand, what's the domain? That's not given. We're going to have to work it out for ourselves what the domain is. We're going to have to draw the picture and infer from the picture, okay, so that means our domain is what? The other thing is, notice this question does not say find the volume under a surface. Right? That's what we heretofore know how to do, is volume under a surface. Volume between a surface above the xy plane and the xy plane. And that's all we've really done. Now, reminder though, what we really know how to do, and that was just an example, what we really know how to do is compute Riemann sums. Riemann sums are, take your question, chop it up into pieces, and on each piece, identify what function is being multiplied by size, and then that's your integrand. Okay, so a couple of things we're going to have to keep track of here. Here's our picture. Here's the two surfaces. The first surface was the plane z equals 4. Second surface, this paraboloid, z equals x squared plus y squared. And you draw the picture, and we get a pretty clear image in our mind of what this thing looks like. This volume that we're trying to find is this thing right here. Wish this had like a fill-in feature, but oh well. Okay, so that's the volume we're trying to compute. Is everybody on board? Okay. Now, so if we look at a little piece of area down here, and let's say I look at this little tiny little piece of area right there, what volume is associated to that piece of area, I ask. And I'm going to associate volume to area by saying, look, hopefully it comes as no surprise, but I'm going to take this thing and I'm going to chop perpendicular to the y-axis, and then I'm going to chop perpendicular to the x-axis, and I'm going to end up again with a bunch of french fries. Just these french fries are suspended up in air as opposed to sitting down on the pan or whatever. But anyway, the volume in question is the volume of that was no good. This thing right there. And that volume is a little oddly shaped rectangular box, approximately, again, not exactly, it's got a little curvature at the bottom. But approximately a rectangular box. Rectangular boxes are still, it remains, height times the area of the base. And so here in this case, I mean, yes, that's something times area. It's just that something isn't just exactly one of the values of the function. Now, that something, that height, is different. The key point, though, is we do have something times an area, and so therefore this is going to be a double integral, and the double integral is going to work out. We just have to figure out what that height is. So the height, I hope it comes as no surprise. Let's see here. I'll use blue here. There's a z-coordinate at this point, and there is a z-coordinate at that point. The height that I'm interested in is this distance. That distance, well, these points are straight up on top of each other. They're above the same x comma y. So the distance is just the difference of these two z-coordinates. The z-coordinates are given by these functions. So I'm just going to subtract these things from each other. Everybody happy? So it's like you might recall problems analogous to this back in Calc 1 classes, Calc 1, Calc 2, who knows, where it depends on your course, I suppose. But where you take, if you want to know the area between two curves, then you do an integral of f minus g. Right? That's kind of the same sort of thing here. Do be careful, please. It's really tempting to say, oh, okay, so it's the higher one minus the lower one, so it's this one minus that one. But that's just how I wrote it on the page, right? Importantly, this higher one is the plane. The lower one is the paraboloid. So it's not, you're going to have this urge to say x squared plus y squared minus 4. It's the other way around. It's 4 minus x squared plus y squared. Okay. All right, so there's our integrand. That height, 4 minus x squared plus y squared. Don't forget to distribute the minus. Really easy to mess that up. Okay. All right. Now, next question. What's the domain? Looking at the picture, again, a geometric appeal. The domain is going to be the set of points down here that you might say are the shadow of the solid that we're actually interested in. There's our solid. So we're looking for the shadow of this thing. Everybody happy with that? Geometric appeal. Here's another way to think about that. The boundary of our domain is going to come from, think about how shadows work, is going to come from this lip, if you will, of our solid. Just again, geometric appeal. The paraboloid kind of keeps going outward. That parabola doesn't come in like a wine glass and have a lip that's sort of on the inside. This is a glass that just keeps going outward. I don't know what kind of glass that would be. Water glass. I don't know. I guess it depends. Anyway, so what we want to know then is I want to know really what are the values of x and y. What can I say about x and y on that lip? Well, this lip is where. Let's see here. Colors. This is where that value of z for a given x and y. Here, let me just do it over here. Where this value of z, the value of z on the paraboloid, is equal to this value of z, namely the value of z on the plane. Right? So what I want to know, this lip that's going to define my domain, as being the boundary of my domain, that lip is where the blue height is equal to the red height. Namely, it's where this is equal to that. So it's where x squared plus y squared is equal to 4, and I have a disk of radius 2. Well, the boundary is a circle, but then my domain is a disk of radius 2. Everybody see the reasoning there? Got to do it from the picture, right? The picture is the point. On an exam, just FYI, minus the picture, if you just say, well, I've got these two surfaces, and I guess I'll just, with, minus, no picture. If you just say, I guess I'll just set this equal to that, that's not a clear line of reasoning, right? You got to explain what's, you could put a couple of words into that if you'd like, right? But I do need to see some explanation of why are you setting those things equal. It's not otherwise clear. Okay, so there we go. We've got our domain. We've got our integrand. The domain we know in sort of broad terms, but let's reimagine our domain more conveniently. There's no need to look at that complicated three-dimensional picture. Here's our domain, where x squared plus y squared is equal to 4, as previously argued. And the slicing process for this, now you can go in either order you like. It doesn't matter. No particular reason. I'm going to go and do my y slicing first. So you might say the y slices will be on the outside. Y is going to go from down here to up there. What do I know about these points? Well, they're on. I can see what curve they're on. What the curve they're on. The algebra of the curve is in this case going to be exactly what's going to tell us what those y values are. But the knowledge of this, the geometric characteristics of this curve is what's going to do it for us. This being as it is a circle, this point, the lowest y coordinate on a circle of radius 2, that's going to be negative 2. Okay? And you don't have to do a bunch of algebra to justify that. But you can, if you want, you could further say, hey, and this point, not only is it on this circle, but it is also on that line. And if you take this, and again, don't forget, we're solving for what we want. We want to know y. Solve for y. Given that x is equal to 0 and x squared plus y squared is 4, then you know y has to be either 2 or negative 2. And I'm looking for a lower bound. The lower bound is obviously negative in this case. And so negative 2 is the only reasonable candidate. Okay. How we doing? Is everybody happy with the... Okay. Notice how the specifics are a little different, but... Okay, upper bound. Same story. This point. Same curve. X again equal to 0. Same argument. Just that now we pick the upper bound to be positive 2. Okay. And there we go. So our y bounds are negative 2 to 2. Okay, now for a given value of y, we've got to proceed now to looking for the x bounds. What are our x bounds? We're going to fix a value of y. Green. We're going to fix a value of y. For that fixed value of y, now I want to know what's the range of values of x. Well, x, the lower bound is based off of that point. That point is on that curve. That curve has that equation. There's our usual argument. Right? I'm interested in x. So I need to solve for x in that equation. And so I get plus or minus square root of 4 minus y squared. And now, again, notice this is a lower bound that I'm interested in. Do I pick the plus or the minus of the square root of 4 minus y squared? Well, in this case, the lower bound is clearly, look at the picture. Here's where x equals 0. This lower bound is clearly to the left of that. I have to pick a negative value. So it's got to be the negative square root of 4 minus y squared. Okay. Upper bound, again, highly analogous. Upper bound, that points on that curve. Curve has this equation. Again, solve for x. Same game. Pick the positive one. Okay. So my x bounds are that and that. The y bounds still, of course, negative 2 to 2 as previously noted. Everybody on board? Yeah.
The first integral or the outer, I guess, the outer integral always have a definite number? Like
yes. Yeah. That's right. So let me say that a little bit differently. The inner bounds may and presumably should, but unless you have a nice, pretty rectangle, in which case everything's a constant. But usually, the inner bounds usually will depend on the outside variable. The outer bounds, there is no further to the outside variable for them to depend on, and so they have to be just numbers. Asterisk if the statement of your question has, some ambiguity, like if it's not a circle of radius 3, if it's a circle of radius r, right? Then of course that might appear in your bounds, but the point is that's intended to be a constant. Great question. Anybody else? Okay. All right. So, which order should you slice? You'll notice I made some arbitrary choices here. For no reason that I explained, I chose to do my dy slicing first, and I'm going to say first here. Let me take a quick sidestep on one thing. I did my y slicing first, but just a reminder. While in the slicing process, y came first. When it comes to actually evaluating this iterated integral, you do have to go from the inside. So it's when you start cranking out the integral, you do the x integration first, right? So the terminology, which variable comes first, it's a little ambiguous, right? So somebody, I think it was you, already made use of the terminology that I like to encourage, and that is outside versus inside. It's completely unambiguous. Right? The outside integral is the one that's the first in the slicing, and it's last in the integrating. It's always that. So, unambiguous, and that's convenient. Anyway, okay, that's it. Which way should you do it? Why did I do it dx dy? Why didn't I do it dy dx? This being our picture. And the answer in this case is that it would not have mattered very much either way. I could have done it the other way. It'd be just fine. Okay. Different details, but it would be just fine. Do notice, though, that in this case, if you did do a switch, right, you can't, hand wave, you can't do this. Right? This is a curiosity of rectangles that you can do this because they're constants. Neither one depends on the other, and it's just a really simple scenario. But here, if you switch the dx and the dy, if dx is on the outside, then dx will have constant bounds. It would not make any sense to have the dx on the outside and then have the dx bounds be functions of y, which is further to the inside. That doesn't make any sense at all. Right? So you would have to completely redo the bounds. They would end up looking highly analogous to this. But again, very importantly, this is not how it works except for rectangles. Okay. All right. So how do you decide which order to go in? Would it have been equally convenient for this problem if I had done the other order? Is it kind of a toss-up? And I claim no. I claim on this one there was really important. I kind of hinted at I think I said asterisk at some point along in this discussion. It's really important to do your x slicing first, to do the dx on the outside for this problem. And I want to go through and show you why, exactly what it is that's so important about this. And furthermore, how you guys can detect, how you can anticipate which one's going to be most convenient for you as you look at some other different problems. Okay. So we're going to look at the same question now and slice it in the other order and see what happens. And here we go. Okay, so here's our, you can ignore this over here for the moment. So here's our domain. Right, the domain's what's in between those two parabolas. And let's talk about the range of values of y. We're going to do our y slicing first. So y is going to start, well, there's the first value of y. There, it's easy to see that's where y is equal to 0. Y ends at that point, which you can easily see is y equals to 2. And so, yeah, no problem, right? Where's the problem? This is looking really easy so far. Started off by saying, here we go, y goes from 0 to 2. Okay, we just have to figure out what these x bounds are now. So let's go back up here to this picture. What's the range of values of x? We'll fix a y. Think about the range of values of x. So here's a choice of y, x. Then, well, let's see, it starts at that point, ends at that point. What's the problem here? Again, it seems, I mean, I can see the curve. The curve has an equation. You just find them. What's the problem? Here's the problem. That is a valid argument for, to keep in mind, y is going from 0 to 2, right? This is a valid analysis for these values of y. But for these values of y, it's not. For those values of y, let's take, for example, that value of y. Then, here, let me make a better choice. Come on. That value of y, that's the range of values of x. It's based on those points which are on a different curve. They're on that curve, not this curve. So that's a tremendous problem, right? The formula for x1 is based off of that curve for small values of y, but it's based off of that curve for large values of y, which is what I have in this picture over here. Why don't I just do it over here as intended? So value of x1 is based off of that curve for large values of y. Different formulas. No surprise, because they're different curves and they have different formulas. When you solve for x, you get different answers. Right? If you solve for x in this first curve, you get square root of y, plus or minus. If you solve for x here, you don't. You get square root plus or minus of 2 minus y. So which is right? Which one do you use your bounds? Well, answer, you can't use either one as I have it set up. I can't proceed allowing y to be thought of as simply going from 0 to 2. I get then, because of that too broad a range of values of y, I get conflicting answers for what to put in my x bounds. I've got to break it up into 2 separate integrals. This is super annoying. For values of y between 0 and 1, let's come back up here. For values of y between 0 and 1, I can reasonably say that, okay, well, the lower bound and the upper bound, they both come from this curve. That curve has that equation. Solve for x, and I get those bounds for x. But that's only valid for y between 0 and 1. I then have to come back up here and say, okay, yeah, and then, okay, fine, for these values of y between 1 and 2, as y goes from 1 to 2, it is these points that determine bounds, those being points on this curve with that equation, solve for x, and my x bounds are that and that. And you just can't combine, I mean, it's tempting to want to say that you have a single integral, y goes from 0 to 2, but you just can't combine these integrals like that because what's on the inside is different. So this is what you get. This is your alternative. If you slice the other way, right? So let's decide now, which one do we like better? I'm being deliberately silly. Do you want to work out 2 nested intervals? Or if you just slice the other way, right, like this, do your x slicing first, no problems, and you get a single iterated integral. Well, nobody wants to do more work, I assume. We want to do it the easiest way possible. By the way, here's another ugliness. Notice in this integral here, look at these bounds. Constant on the outside, well, of course. On the inside, polynomials. Fine. As far as functions go, not that bad. Right? Let's anticipate what's going to happen when I start to crank out this integral. When I do the dy integral of this integrand, I'm going to have, there's going to be an xy, and there's going to be a y squared, and into those into the y's that appear in this integral, I'm going to have to plug in these for the y. So I'm going to be taking polynomials and putting them inside of polynomials, which gives me polynomials. So my x integral is going to be an integral of polynomials, which is fine, no problem. On the other hand, what's going to happen here when I start cranking these out, and let's just look at this one over here for no particular reason. I'm going to have y's and y squareds in the antiderivative, x's and x squareds that are in the integrand, that are in the antiderivative here. Into those x's, I'm going to be putting square roots. Okay, now, if I put the square roots into where there's going to be an x squared, fine, the square root disappears. But there's just going to be a 4x here. There's going to be just a yx here. And so I'm going to have, in the integrand of my y integral, there's going to be square roots in there. And it's not that we can't do that, but it's just, it's less ideal. Nobody would prefer to do that, I would assume. So it's another undesirable thing about doing the slicing in this direction. Yeah? Okay. So, in this case, clearly we want to do the slicing the other way, like we did the first time. Okay, so how do we anticipate this? Do I have to go through this process every single time and then compare and contrast and decide which one's going to be easier to work out? I suggest no. Let's talk about what is it that made me have to break. Let me use a better color. What is it that made me had to break this thing up? At y equals 1. I had to break it up at y equals 1 because that's where these defining points, lower bound defining point, the upper bound defining point, sort of jump from one curve over to the other curve. Right? Let me say that a little bit differently. I had to break it at y equals 1 because y equals 1 is where these two curves intersect. And it's because they intersect that the point that defines the lower bound can jump from one to the other. Well, a slight variation of that is, look, where two curves intersect, you have a corner. I'm going to loosely call a corner, if you will. It doesn't have to be a sharp corner, but there's what I'm going to loosely call a corner. And so, roughly speaking, the anticipating trick is this kind of thing is going to happen where you have different formulas for your inner bounds when your slicing process slices through a corner. So here are the corners in our domain, right? Our otherwise domain is this whole thing. On that thing, there aren't any corners. There's no corners up here. There's no corners down there. The only two corners are there and there. Let's get rid of all of this. Right? And as I slice in the y direction, naively at first, thinking, oh, this is great. Y goes from 0 to 2. I just sliced through a corner. In that process of slicing through a corner, you should sort of say, okay, look, that means that there's two curves. That means that the bounds can jump from one to the other. Oh, gosh. You know what? This is going to be two separate intervals. So before you begin your slicing, before you make your decision, which way to go, identify your corners. Think about which way would you slice to avoid slicing through corners. And notice if we do it the other way, like we did the first time, you start at a corner, but that's no problem. You had to start a new integral there anyway. throughout the process of slicing, doing your x slicing first, you never hit a corner. Now, you end at a corner, but again, you had to end your integral there anyway. There's nothing left to go to, so I don't need to start a new integral there. Yes?
Would there be a problem that you do relative unavoidable?
But yeah, sometimes, sometimes life is brutal. And so this is a motivational sort of like, this is for your consideration. I can't promise that it'll always be, so for example, what if your domain might be a octagon, and then you're just out of luck. There's corners all over the place, and it's going to be hard. Yeah. Okay, so try to avoid corners is the big lesson there. The other thing, there's a second lesson here. Remember, I was complaining about the fact that we had these square roots in the bounds. And all else being equal, kind of prefer not to have the square roots. How can we avoid the square roots? More generally, how can I avoid uglier inner bounds, which will lead to uglier outer integrals? And this is another thing we can kind of trace back, right? Let's look at the original curve here. The original picture and the original curves. Notice I wrote this as y equals x squared. I guess I could have written it as x equals plus or minus square root of y, but that would have been uglier, right? So what you've got here is an indication of the fact that I wrote this as y equals x squared kind of suggests that it is more easy to think of y as a function of x than it is to think of x as a function of y. So when you go through your slicing process, don't put yourself in a situation where you're going to need to solve for x as a function of y. Said differently, don't put x on the inside. Okay? Put y on the inside. Whatever you put on the inside is what you're going to have to solve for. I would like to solve for y, all else being equal if I have a choice. Right? So likewise up here, it's a lot easier to solve for y than it is to solve for x. So let's put the easy one to solve for, y, on the inside. And again, it is breaking that rule. It is the fact that I put the x on the inside, effectively, that forced me to have to solve for x and therefore got me into trouble with these square roots. Okay, so those are these two observations that I made down here, and a couple of examples. This one here. I mean, that's kind of ugly, right? I mean, there's no way to avoid corners with this. But do notice that because of where the corners are and the fact that these two corners have the same coordinate, if you slice it up on the outside with y going from 1 to 4, you only have two separate chunks. Whereas if you do it this way with x on the outside, you're going to have three separate chunks. And, I like 2 better than 3. Okay. This is a monster. If you slice this up with y going from -2 to 1, and again, you can do that, I suppose, but, oh man, what a brutal, there's two corners right here, so here's going to be your first integral is going to be on this, and then notice for all the values of y up here, right, for that value of y there, you're actually going to have 3 separate ranges of x. Therefore, in effect, you're going to have a grand total of 4 separate double integrals if you slice it that way. Right? So again, the way to avoid that is, the way to minimize that is let's do the x slicing on the outside. I am still going to slice through this corner, right? But then the point is, my two different integrals are that one and that one. And all else being equal, I'd rather do 2 integrals than 4 integrals. So, yeah. Okay. All right. Moving along. Let's talk about the next kind of integral. Well, a bunch of exercises in here, by the way. And I want to segue into triple integrals by sort of summarizing what we've done so far. We revisited single variable integrals, and quick reminder, single variable integrals, a couple different applications of single variable integrals. You can use single variable integrals to compute the area under the graph of a single variable function. Everybody's first and favorite example. Except for me, I guess. But another application, another thing you can do with single variable integrals, you can compute the mass of a one-dimensional rod of metal, let's say, as we always do. And now let me remind you that there is a different point of view you can take on these two applications. You can think of these as different visual metaphors for single variable integrals. So in your mind, when you think about, okay, what is a single variable integral? You can think of it as, oh, I'm adding up a bunch of little areas. And the integrand represent height. Or, alternatively, you can think of it as, oh, I'm adding up a bunch of little pieces of mass, and the integrand represents density. Now, at this particular moment, I suppose and assume that you're all thinking primarily your cornerstone, your sort of what you hang your hat on, the way you think about integrals is probably this. And sure, of course it is. That's the way Calc 1 and 2 classes kind of run. I'd like to encourage you to think of it more this way. For intuition purposes, think of it as, and by the way, just for the record, when you do an integral, the integral is defined on a domain. That domain is one-dimensional. That domain is from A to B. This application here, thinking about how mass accumulates, is on the interval from A to B. There's something about this that's arguably a little bit more directly relevant to what Riemann sums are. Arguably. And this, you could, from that point of view, then say, oh yeah, well, if I think of the integrand not being how I keep track of stuff that's accumulating along the actual interval itself, but somehow it's accumulating above the interval. Weird. Then let's interpret the integrand as being height instead of density. One could argue that this is the really kind of the slightly strange one. Okay, so old news. Here are those same pictures again. Well, here are the analogous pictures again, this time for double integrals. Let's see, I would kind of like for these to both be on the page at the same time. Let me zoom out a bit. I think my writing is big enough. For double integrals, we have the same choice, right? And of course, there's many other applications. But you can think of double integrals as being a way of, fundamentally of computing how much volume is under a surface, or you can think of double integrals as computing the mass on a two-dimensional region, or the amount of stuff of whatever description. Maybe it's not mass whose density we're integrating. Maybe it's population whose density we're integrating, or concentration of some chemical, whatever, that we're integrating. And again, there's this temptation to, well, this is the one that looks like that, and this is the one that I've known for a couple of years now. And so there's a temptation to want to think of integrals this way, from the graph point of view, the geometric, the size, how much stuff is under a graph, because of familiarity. And again, I want to push for this one. I want to encourage y'all to start thinking more in terms of an integral is a Riemann sum. Riemann sums happen on domains. Here is an application that's literally happening on that domain. Okay, so now I can make the case for why I think this is, I think it's important for various reasons, and I think the case I just made is a pretty good one. This is more directly related to what Riemann sums are. But here's where you're going to start to work. Here's where you really have to take this seriously. We've defined a Riemann sum on a one-dimensional domain. We've defined a Riemann sum on a two-dimensional domain. Why stop there? Right? We live in a three-dimensional world. there's all sorts of three-dimensional domains on which I might want to add stuff up. Right? It makes loads of sense. And so we're going to momentarily, we're going to define something called a triple integral. And what do triple integrals look like? Well, if you insist on thinking about integrals from this geometric point of view, I don't know what to tell you. Right? I mean, look, let's notice the pattern. If you insist on thinking of single variable integrals from the point of view of, well, it's an area under a graph. Well, the graph of a function of one input variable is a two-dimensional picture. Down here, volume under a graph of a function of two variables. If you have a two-dimensional domain, function of two variables, you have a three-dimensional picture. Well, following the pattern, if you wanted to, by extension, think of triple integrals, integral over a three-dimensional domain, function of three variables, you have a four-dimensional picture. I can't help you with that. Okay, so this is a crash and burn situation that we've got ourselves painted into, and it's a problem. Right? Whereas, again, if you think about Riemann sums or integrals from the point of view of this mass metaphor, no problem. Okay. A single variable integral tells you how much mass accumulates along a one-dimensional domain with a one-dimensional notion of density. Double integral tells you how much mass accumulates on a two-dimensional domain with a two-dimensional notion of density. What's a triple integral? Yeah, it's just telling you how much mass there is inside of a three-dimensional domain, assuming a three-dimensional notion of density. In other words, we're back to the old middle school notion of density as being mass per unit volume. One could argue that this picture, this intuition for triple integrals is arguably more, relatable than these are because the notion of density is more familiar. So, anyway, something to worry about. So, I'm a big fan. Well, I'm a big fan of the idea that you should understand all these perspectives, of course. Right? I want you to be able to think about integrals in all these different ways. What I think is a mistake and a problem is if students say, all right, I'm going to continue to think of single variable integrals this way and double integrals that way, and I guess, okay, fine, I guess I'll think of triple integrals this way. And now you're mixing your metaphors, right? And that's going to lead to a lot of confusion that, well, mysteriously for some kinds of problems involving volume, it's a double integral, but for some kinds of problems involving volume, it's a triple integral. And it's, why is that? Well, it's because you're mixing your metaphors. Everybody see the problem? All right. Okay. Okay, so I would encourage, in addition, and I don't expect everyone to just abandon this idea of how integrals relate to graphs. Of course, it's very nice. It's very convenient in certain circumstances. But I would like to encourage you to think more in terms of integrals from this point of view. It's probably the one that you need to build up the most. Probably the one you sort of let done the least amount of thinking in terms of. If only so that you can have a reasonable build up, a reasonable segue into how to think about what triple integrals are. Okay, so triple integrals are going to be where we're going to take, instead of a one-dimensional region or a two-dimensional region, instead of on those regions, chop it up, add it up, we're going to take a three-dimensional region. Chop it up, add it up. Here's a picture. Let me go back to this. Whoops, wrong picture. Here we go. Here is a three-dimensional domain. Right now, we're starting with a rectangular box. This rectangular box, maybe I want to compute the amount of mass inside of that box. And this is it's not an empty box. This is a solid box that's got, some sort of, it's got a bunch of dirt in it, but the dirt's got a certain amount of water, and there's more water at the bottom, but it's also it's kind of muddy in the middle, and then it's just kind of dry dirt on top. And so the mass density is varied throughout this. Maybe there's some rocks in it in various places, right? So the mass density is wildly varying over the size of this box. And what's the total mass? Well, golly, that's a hard problem. But what I can do is chop this box up into little pieces. On each little piece, really little bitty piece. By the way, I chop that way, and this way, and this way. Right? Get a bunch of little bitty boxes like that. That's a teeny tiny itty bitty little box, and in that teensy weensy little box, there's not much movement. There's not much space in there, and you expect the density here and there to be, well, they're pretty close to each other, so the density should be pretty close to each other. Assuming the density is continuous, then it would be, at least for the purposes of the limit. And on that little box, the mass is just the volume times the density. So we're going to be adding up a bunch of terms, just like with single variable integrals, just like with double integrals. The terms are going to be something times size. In this case, size is volume. And that leads to an expression that looks like this. It's a Riemann sum. Again, this is just kind of a formal way of writing down what I like to summarize as chop it up, add it up. Taking our box, we're chopping it up into little pieces. On each piece, we see what we got, and then we're going to add up what we got on those little pieces. Okay. Being as it is a Riemann sum, this is going to be our definition of a new kind of an integral. This is what we call a triple integral. It's a triple integral because the domain is three-dimensional. The integrand is a function of three variables. It is a three-dimensional notion of size that we're talking about, right? This is very decidedly not a double integral. Obviously not a single integral. And the notation, I think, is very believable. Three integral symbols instead of two because of all the, because it's a three-dimensional everything, right? So pretty natural notation. Note that delta V we're going to shorthand as dV. Okay. All right. Questions before I go on? We're going to do a bunch of applications, a bunch of examples. Okay. First application. Suppose I want to compute the mass in a solid rectangular box. Well, the total mass is the sum of the individual pieces of mass that I get when I chop into a bunch of little teeny pieces. On each piece, mass is density times volume. Oh, hey, check it out. I have a Riemann sum that is exactly the definition that I made earlier on this page of an integral. And so I can compute this mass with a triple integral. How we doing? Everybody good? Still don't know how to compute these things, but we'll get to that. A reminder, again, it is a highly common, and I encourage this notation, this sort of shorthand notation that leads you to write down things like triple integral dm. Just make sure to remember that this is just a shorthand for this. Don't make the mistake of thinking that there's an m-axis somewhere, right? There isn't. That's not what this isn't. Dm does not mean distance along the m-axis. Dm is just a shorthand for a little piece of the object in question, namely mass. Okay. All right. Suppose you want to know how many bacteria there are in we've got an aquarium, let's say, and there's a bacteria floating around, and we know the density at different places in the aquarium. How would I compute the total number of bacteria? Well, total population is the sum of the local populations. In each little locale, population is population density times volume. By the way, here population density is population per unit volume, because bacteria live in volume, they don't live on area. Oh, hey, check it out. That's exactly the Riemann sum from earlier in this page, aka it's an integral. Said differently, I can compute the population with that triple integral. Again, you can shorthand it like this. Again, this only is intended to be a shorthand for that. There is no p-axis, and it's fine to just write your development of your integral like that. Okay. Everybody happy? Okay. How do we compute these triple integrals? Now, let me remind you how we proceeded when we were talking about double integrals. The punchline was we can compute a double integral as a nesting of single variable integrals. And the way I motivated that was going back to the volume picture. Right? I wanted to give a geometric sort of intuition, a sense, and I hope you have a reasonably good geometric sense for why it is that double integrals, as a way of computing volume, for example, and iterated integrals, also a way of computing volumes, kind of should be the same because, come on, they're addressing the same question, and they just look the same. Well, I can't do that for you here because, again, we have a great big question mark. If I were to interpret this triple integral as computing, suppose we have a function of three variables, and I want to make the graph of that function of three variables, 3 inputs, 1 output, I've got a four-dimensional picture. And look, if we were four-dimensional mathematicians writing on three-dimensional paper, which is very hard to visualize, but if we were, then I could make that argument. But we aren't, so I can't. And so there is no such picture. What I am going to, the appeal that I'm going to make to y'all is, but it works out the same way. Right? So, if you have a triple integral that's motivated per any of the previous discussions, mass, population, whatever, you can compute that triple integral with a corresponding nested integral, where the range of values for z are the bounds on the z integral, and the range of values for y are the bounds on the y integral, and the range of values for x are the bounds on the x integral. So this is just an appeal by analogy, you might say. Or said differently, this summation in the triple integral has to be a summation over the entire box. So I need the ranges of values of x, y, and z to allow me to range over all possible ordered triples of x, y, and z. Namely, the x, y, and z bounds have to go over all possible values of those three variables. I think this is pretty believable. Okay. Do notice that since we have three differentials instead of two, we're no longer limited to, well, here's our two choices of which way to do our differentials. You can either do dx dy or dy dx. Well, there was only two options because there's only two ways to order two things. When you have three things, there are actually six different possible ways to order those differentials. You have six different ways to slice it. So no matter how you slice it, it takes on a very more complicated meaning when you're talking about triple integrals. So this is both bad news and good news. Good news, you have a bunch of different options to choose from. Bad news, you have a bunch of different options to choose from. So, anyway, more options to consider, but more flexibility of in calculation. Okay. All right. Let's see here. Okay, you know what? This is a pretty good stopping point. Why don't we take a pause right here, and we'll pick it up at 11:15. Okay. See y'all in a few minutes.